Hi everyone. In this screencast, I'm going to be talking about atomic radius. So, the atomic radius is defined as the distance from the nucleus of an atom to the edge of that atom's electron cloud. And we measure that by taking a diatomic element like H2, measuring the distance between its two nuclei, and then dividing that by 2. This image shows our change in atomic radius as we move either across a period on a periodic table or down a group on a periodic table. So you can see up top we have our different groups on our periodic table, 1 through 8, and on the left we have our different periods. And if we look at period 2, for example, we can see that as we move from left to right across this period, our atomic radius is decreasing. The size of these atoms is getting smaller. And that's true as we move from left to right on any of these periods. If you compare that to our trend as you move down a group, when you move down a group, your atomic radius increases. So if you compare hydrogen to lithium to sodium to potassium to rubidium and to cesium, the atomic radius is increasing each time you move down the group. So how can we explain this trend using shielding and effective nuclear charge? Well, when we move across a period, we've learned that the shielding does not change. And down here we have Bohr diagrams for sodium, aluminum, and chlorine. Notice in each of these Bohr diagrams, sodium, aluminum, and chlorine all have 10 shielding electrons. That's because they're all in the same period. However, as we move across a group, the effective nuclear charge is going up because the number of protons in the nucleus of sodium, aluminum, and chlorine increases as you move from left to right on the periodic table. So chlorine has the highest effective nuclear charge because it has the most protons in its nucleus, 17. And therefore, it's going to attract its outer electron more strongly than aluminum or sodium. And that outer electron is going to be pulled into the nucleus, making the radius of chlorine smaller than the radius of aluminum, and the radius of aluminum would then be smaller than the radius of sodium, because as effective nuclear charge increases, those outer electrons are pulled in closer. Well, what about down a group? Down a group, our effective nuclear charge is staying the same, but our shielding is increasing. And when there's more shielding, outer electrons are held less tightly. That is, they feel the force of the nucleus less. So lithium's outermost electron is held very close to its nucleus, whereas sodium's is held less close, and potassium's is not held very tightly at all. And that's because as you move down a group, there's more shielding. So sodium's outer electron is able to move further away from the nucleus, and therefore sodium will have a larger atomic radius than lithium, and potassium will have a larger atomic radius than sodium, because as you move down a group, there is more shielding. How can we connect shielding and effective nuclear charge to Coulomb's law and use all of them to explain atomic radius? Well, we should recall for Coulomb's law that F is the force of attraction, Q1 is the magnitude of our charge, which is really equivalent to Z effective for our examples. And R is the distance, which for us increases with the number of energy levels in an atom. So to explain why atomic radius decreases as we move across a period, well, when we move across a period, effective nuclear charge is increasing. which means that this number, Q1, gets larger as you move from left to right. And because it is directly related to the force of attraction, the force of attraction also increases, and those valence electrons are pulled in closer, giving the atom a smaller radius. Okay, what about moving down a group? Well, when you move down a group, the effective nuclear charge is not changing, but the distance does change. So, if we move down a group, the distance between my outer electron and my nucleus is increasing, and that's because there are more energy levels and more shielding. So this number is getting larger as I move down a group, but my effective nuclear charge is not changing. This means that my force of attraction is going to get smaller, because there is an inverse relationship between force of attraction and the distance between those outer electrons and the nucleus. So, as I move down a group on the periodic table, force of attraction will decrease, and those outer electrons will be able to move further away from the nucleus, increasing the atomic radius.